Good day everyone! Today I'll be providing a high-level overview of our research whose goal it is to contribute to solving the AI alignment problem. The key pillars of our research agenda are first, searching for features in neural networks, second, developing unsupervised methods for finding particular features, and third, studying the fundamentals of language model cognition. We think that our work is important in two ways. It is a helpful building block toward the ambitious interpretability goal of completely reverse engineering a neural network. And second, it will hopefully yield tools that let us check whether a model is thinking about problematic things, which we could ideally ablate or edit out. To that end, we're currently focusing on eliciting and understanding latent knowledge in language models and neural networks more generally. Our work started as an extension of the contrast-consistent search method and now concludes neural network interpretability more broadly. In addition, we aim to help the field grow through mentoring and communicating relevant ideas through videos where we distill important ideas of papers and research directions. The contrast-consistent search method, or CCS, is an important component of our research. It seeks to answer yes-no questions based on unlabeled model activations, providing an approach to extracting information from large language models that does not rely on the model's output. This unsupervised approach is important to AI alignment because we want reliable tools that let us predict whether a model is being truthful. The procedure works as follows. First, we generate contrast pairs by attaching pseudo-labels yes and no to a sentence. Second, we extract hidden states or model activations at a particular layer. Third, we train a linear classifier to map the model activations to the probability of being true. Intuitively, the direction along which our classifier achieves the highest classification accuracy serves as a proxy for the truth direction we hypothesize the model to represent internally. This is done by optimizing an unsupervised loss function that incentivizes consistency and confidence of the probability predictions. An important detail which has a large effect on how CCS performs, especially on autoregressive GPT-style models, is a particular way of normalizing the model activations before learning a linear probe to identify the truth direction. It would be easy for a linear probe to pick up on the cues provided by the pseudo-labels in the contrast pair. To avoid the linear probe from doing so, we normalize the activations of the contrast pairs. A reasonable approach would be to normalize the data over all prompts. In re-implementing the original results, we and several other research groups misinterpreted the paper and its associated code before arriving at an important realization. The correct way to normalize the data is per individual prompt and not over all prompts. There's a more general important distinction to make here. Removing the ability to linearly predict a certain property, like the pseudo-label, is not the same as eliminating all information about that property. This raises an important question. How can we eradicate all the pseudo-label-like information from the extracted activations? One possible approach could be to cluster contrast pairs into a few types and then eliminating the pseudo-label direction for each type. These and related thoughts led to the development of a new method called variance-invariance negative covariance, or VINC for short.
The development of VINC was spearheaded by Nora Belrose and Alex Mallon, to whom we want to extend our gratitude.
We hypothesize that the probability of a sentence being true should not change if we paraphrase that sentence. So, we augment our data by paraphrasing existing sentences. This leads to finding a truth dimension that is more robust and invariant to small changes in the prompts. We use principal component analysis to identify the directions of maximal variance. The first principal component is chosen as the direction along which to do the classification so that the contrast pair activations are most negatively correlated. Our work started out as a reproduction of the results in the paper that introduced CCS. This then developed into an open source project we're building in collaboration with Eleuther AI. This open source contribution allows other researchers to leverage the tools and insights we developed for their own investigations. The ELK library provides functionalities such as extract, elicit, eval, and sweep. These features streamline the processing of model activations, training of linear probes, called reporters, evaluation of accuracy, and analyzing results for comprehensive dataset and prompt template combinations. The library is easy to use from the command line. Here's an example. If you call elk elicit GPT-2 IMDb, this extracts the model activations, trains a linear classifier, and produces summary statistics like the OROC score and accuracy. You can also do sweeps over a range of datasets, models, and prompt combinations with the sweep command. As an extension of our CCS work, we have mentored students of the Supervised Program for Alignment Research, with whom we have investigated the effectiveness of a probe trained on model activations across different languages. The question they asked was the following: does a probe trained on model activations generated from data in one language generalize to a different language? Results of this work show that models are capable of zero-shot generalization to tasks in languages they have never seen before. In addition to the research presented so far, we have written a paper titled Decomposing Activations into Feature Vectors. We start our investigation with the assumption that activation vectors are linear combinations of feature vectors and examine approaches in the literature for finding a good decomposition. The approaches we identify split into two parts according to how the number of features compares to the dimension of the activation space. In the first part, we examine methods applicable in case the number of features is smaller than the dimension of the activation space. These include singular value decomposition, principal component analysis, and non-negative matrix factorization, NMF. In the second part, we discuss methods applicable in case the number of features is large. In other words, when the model holds features in superposition. We review work on taking features out of superposition with sparse autoencoders. You can find out more in the associated YouTube video on our channel. Complementary to writing posts on Less Wrong and writing papers, we have started to extend our research communication to a wider audience through our YouTube channel. We explain key concepts, discuss results, propose future experiments, and encourage discourse within the scientific community. In the upcoming months, our main research objectives are the following: figuring out whether CCS is measuring truth, combining CCS with model editing, and extending CCS. In particular, we're interested in creating a method similar to CCS and applying it to other concepts and other types of models. We could, for example, apply it to a reinforcement learning policy network to find out how to represent the value of a state. This type of research can be useful for detecting deception in the long run. On the operational side, our main focus is to secure funding that will support us for at least a year to come and to identify a permanent location. In the midterm, we hope to work on developing a robust hiring process to expand our team with capable individuals who can contribute to our research. We'd like to thank the teams at Cerimats and LTFF for ongoing operational and financial support. Moreover, we'd like to extend our gratitude to Jake Mendel, Nora Belrose, and Alex Mallon for fruitful collaborations. In our ambition to help solve the alignment problem, we're actively seeking funding and collaborators. Please reach out to us in case you're interested in helping us advance our research. You can email us at research.nottodie@gmail.com and find our YouTube videos on Not to Die Research.